Hi, this is Algebra 1, Lesson 81. We're going to talk about graphical solutions, inconsistent equations, and dependent equations. We're starting on page 330. So this lesson is going to start with a reminder about the degrees of terms and of polynomials. The degree of the term is the sum of the exponents of all the variables in the term. So it's 2 times xy to the fifth. This is going to be the exponent to 2 doesn't count because it's not a variable. The exponent to x is an implied 1. And the exponent to y is 5. So 1 plus 5 is 6. This is a 6th degree polynomial. Okay? 4 doesn't count because it's not a variable, so the power of x is 1, so this is a 1st degree. X times y, this is x to the 1 times y to the 1, so this is a 2nd degree polynomial. Okay? Well, terms. These are actually terms, sorry. Here's a polynomial. The term of a polynomial is going to be the same as the degree of its term with the highest degree. So the degree of this term is going to be 5. The degree of this term is 1. So this is a 5th degree polynomial. Okay? The degree of this term is still 5. The degree of this is 1, and the degree of this is 1. So just like in a polynomial, the degree of an equation equals the degree of the term with the highest degree. So in this case, it's this one, and it's a 5th degree equation. X plus 2y plus 4. This is a 1st degree term. This is a 1st degree term. This is a 0 degree term because there are no exponents. So this is a 1st degree equation. We know that the graph of a 1st degree polynomial equation with 2 variables, like this one, is a line. And we found the solution to a system of 2 linear equations by substitution and elimination. So if we have 2 equations like this, we have solved these by substitution or elimination. I told you as we were doing those that the solutions we found were where the graphs of their lines cross. We can find the solution of 2 equations by graphing them and seeing where the lines meet. If the lines meet at a reasonable spot. It would be very tedious to solve that way if the place where they met were some crazy point like negative 157 and 392. Fortunately, your book is unlikely to give you a problem like that. We will check the point where the lines cross to make sure that both is a solution to both equations. So we're going to start by graphing this. We have y equals x plus 1 and y equals negative 2x plus 4. We're going to use the slope-intercept method of graphing these. Okay, so we're going to start by graphing y equals x plus 1. The slope is 1. Remember, the slope is a coefficient before the variable x, and there's nothing here, so it's an implied 1. So the slope is 1, and that means the slope is 1 over 1, so every time the x goes 1 to the positive, the y goes up 1. And every time the x goes 1 to the negative, the y is going to go down 1. It's a positive slope, so the line is going to go up to the right, and our y-intercept is at when x equals 0, y equals 1. Excuse me. Okay, so where x equals 0, y equals 1, And our slope is 1 and 1, is 1 over 1. So for every x to the right, we go 1y up. For every x to the left, we go 1y down. Oops, it's actually here, not there. Never mind that spot. So our line is going to look like this. Okay, when you graph lines, please label your line. So this is y equals x plus 1. Okay. The next one we're going to graph is y equals negative 2x plus 4. So our slope is negative 2 over 1, right? It's a negative slope, so we know the line is going to go this way. For every 1 x to the right, we're going to go down 2. And our y-intercept is at 4. So here's our y-intercept where x equals 0, y equals 4. And every time we go to the right 1, we're going to go down 2. 1, 2. To the right and down 2. Okay, so there are 3 points on the line. Once you have 3 points, then you can draw the rest of the line. Okay, so this line goes this way. We're going to label this line. This line is y equals negative 2x plus 4. And we can see that our lines cross right here. This point is 1, the x coordinate is 1, and the y coordinate is 2. Okay, so that's the place where the graphs of our lines cross. We can check these points in both equations by substituting 1 for x and 2 for y. Okay, so we have y equals x plus 1, y equals negative 2x plus 4. If this is the correct point where both of these lines are satisfied and the lines cross, then this point should give true statements for both of these equations. So let's try it. For y, we're going to substitute a 2, and for the x, we're going to substitute a 1. So 2 equals 1 plus 1. That's true. Okay? In this case, we're going to say 2 equals negative 2 times 1 plus 4. So 2 equals negative 2 plus 4. 4 minus 2 is 2. So that's true. So this is a correct point. The solution for this line is 1 and 2. Okay, let's try another one. Okay, we're going to solve by graphing y equals 2 and y equals x. In y equals 2, there are no x coordinates, so our line is going to be a horizontal line, right? For every x, y equals 2. So for every x, and we can just follow this line, y equals 2. I have a hard time drawing a straight line even when I'm tracing a line. That's pretty sad. Okay, y equals 2. Okay, this one is y equals x. The slope here is 1 over 1. Sorry, the slope is 1 over 1 because that's the coefficient of x. There is no y-intercept, written, which means the y-intercept is 0 and it's going to go through the origin. Okay? So it's going to go through the origin right here, and the slope is going to go up for every, it's going to go up 1 for every 1 to the right. So over 1, up 1. Over 1, up 1. Over 1, up 1. And pull out my handy dandy straight edge. And this equals y equals x. Okay? The point where the lines cross is right here at 2 and 2. Okay? So let's check that. That should be y equals 2. And we're going to replace the y with a 2, and that equals 2 equals 2. And that is true. Right? If y equals x, and the y is 2 and the x is 2, then that's also true. Okay? So this is the point that satisfies both these lines. Okay, let's try another one. We have y equals x plus 2 and y equals x minus 1. So for this line, our slope is 1, because that's the coefficient before the x. So the slope is 1 over 1. It's just a stair step. It's positive, so it's going to be going up to the right. Our y-intercept is at 2. Okay, so that's positive 2. It's right here. And the line is just going to stair step up 1 over 1, up 1 over 1. Okay. So this is y equals x plus 2. Okay. Our other line is y equals x minus 1. Our slope, once again, is 1, because that's the coefficient of x, so it's going to be 1 over 1. It's going to stair step again, up 1 over 1, up 1 over 1. The y-intercept is negative 1. So where x equals 0, y equals negative 1. So that's right here. And it's going to stair step. This is y equals x minus 1. Okay, so it appears from our graph that the lines are parallel and never intersect. This makes sense because the lines had the same slope, but they had different y-intercepts. So they're going to go up at the same rate. They're going to go up and to the right at the same rate, but they're starting at different points, so the lines are going to be parallel forever. They are never going to meet. If they are parallel, no points lie on both lines, so no ordered pair is going to satisfy both equations. An attempt to solve these equations by elimination or substitution will give us a false statement. We call these kind of equations where there are no points that lie on both lines because the lines are parallel, we call these inconsistent equations. You might be able to guess that if these are inconsistent because there are no points that lie on both lines, The kind of lines that do have a point that lie on both are called consistent equations. Okay, so this was an example of a consistent equation. There was a point that lies on both lines. Parallel lines make inconsistent equations. There are no points that lie on both of these lines. Okay, let's look at this graph. We have x plus y equals 2, and we have x plus y equals 3. When you put these back into y-intercept form, we have y equals negative x plus 2 and y equals negative x minus 3. So as you can see, the slopes are both negative. They're both negative 1. So as every time we go to the right, we go down 1. To the right and down, and the right and down. So it's a stair step down. The slopes are the same. The y-intercepts are different. This line meets the y-intercept at 0 and 2. This one meets the y-intercept at 0 and negative 3. So these are parallel lines. There is no point that will satisfy both equations. To demonstrate this, we can solve both of the equations with substitution and elimination. So we have x plus y equals 2 and x plus y equals negative 3. So let's do this with elimination first. So if we multiply this bottom one times negative 1, so we're going to multiply every term by negative 1, which will give us x plus y equals 2 and negative x minus y equals positive 3. Okay, this cancels, we have 0 equals 5. Obviously that's false. And that's what's going to happen if we try to solve equations that graph as parallel lines. We're going to get a numeric answer. There are no variables in here anymore. We're going to get a numeric answer that is false. Okay, let's try substitution. We solved for y here, so let's substitute this into this equation. So we have x plus y equals 2. We have x plus y equals negative 3. That's our series of equations. We're going to substitute y equals negative x plus 2 into here. So we have x plus negative x plus 2 equals negative 3. The x's cancel, and we have 2 equals negative 3. And that's obviously false. Okay, so either by substitution or elimination we get a false numeric answer, which means there are no points, which once again means there are no points in common on these lines. Okay, here's the next one. Determine whether the following set of equations have a common solution. Okay, let's look at both of these. Y equals x plus 2, y equals x minus 1. The slope of this equation is going to be 1. The slope of this equation is going to be 1. The slopes are the same, but the y-intercepts are different. The y-intercept of this one is going to be 2. The y-intercept of this one is going to be negative 1. Therefore, the lines are going to be parallel. We've actually already graphed this. This is the same graph as our graph number 3 right here. We can confirm this by solving the equations by substitution. Okay, so we have y equals x plus 2 and y equals x minus 1. So let's substitute for y, and we'll have x plus 2 equals x minus 1, right? And if we solve for this, we subtract x from both sides and 2 from both sides, and we get 0 equals negative 3, which is false. So our original equations do not share a common solution. Okay, so now we're going to talk about dependent equations. Dependent equations, or equivalent equations they're also called, have the same solution set. So let's look at another graph. Here we have the graph of y minus x equals 2. When you solve for y and put that in the y-intercept form, that's y equals x plus 2. So here's that graph. If we multiply every term in the equation by the same quantity, we'll get an equivalent equation. So if we multiply all the terms in this equation by 2, we will get 2y minus 2x equals, that's an x, equals 4, right? Because we multiplied all the terms by the same equation, these are actually equivalent equations. And if we graphed this, let me get a red marker. If we graphed this equation, if we solved 2y minus 2x plus 4, okay, we need to solve for y, so we're going to get, that equals 4. 2y, we're going to add 2x to both sides and get 2x plus 4, right? And now we're going to divide both sides by 2. We get y equals x plus 2. Okay? The slope is 1. The y-intercept is 2. So here's this, and our slope, 1 up and 1 over, it's the same line. Okay, so this line and this line are the same. Equivalent linear equations are also called dependent equations. Because the lines are the exact same, any ordered pair that's in a solution to one is a solution to the other. And they have an infinite number of ordered pairs that they share, because there are an infinite number of ordered pairs on the line. If we tried to find the solution of a pair of dependent equations using substitution or elimination, the answer is going to be a numeric equation that's true. So for parallel lines, we got a numeric equation with no variables left that was false. For equivalent equations, we're going to get a numeric answer that's true. So here's the same equations we just used, and we're going to determine whether the following set of equations is dependent. So assuming we didn't already know that the graph of these two were identical, we can solve them by substitution or elimination. So let's do this one by elimination. Let's multiply the top equation by negative 2. So we have negative 2y plus 2x equals negative 4. And we're going to add that to this equation. Right? So we just multiplied this top equation by negative 2, all of the terms, to get this. And now we're going to solve it. This cancels, and this cancels, and we get 0 equals 0, which is true. Okay? So, to sum up, Sets of two linear equations with two unknowns fall into one of three categories. We have consistent equations, so our first and second graphs. Here we go. This graph and this graph both show consistent equations. They have a single ordered pair as a common solution. The graphs intersect at one point. So here's where this one intersects. Here's where this one intersects. If you solve these by substitution or elimination, you get a variable equaling, the variables equaling a single number. So x equals something and y equals something. Okay? Inconsistent equations have no common solutions. The graph of inconsistent equations are always parallel lines. So these are graphs of inconsistent equations. If you solve these by substitution or elimination, you get a numeric answer with no variables, and the numeric answer is false. So you get something like 2 equals negative 3. So these are inconsistent equations. Dependent equations are equivalent lines. It's the same equation in two different forms. The graph of two dependent equations is a single line, and if you solve them by substitution or elimination, you're going to get a numeric answer with no variables, but the numeric answer is going to be true, like 0 equals 0. Okay? So here are your three options: consistent equations, inconsistent equations, and dependent equations.